Before we talk about cycloalkane conformations, we are going to take a look at ring strain, which actually provides some evidence about the fact that cycloalkanes do adopt different conformations. By the early 1800s, a number of cycloalkanes were known, but there wasn't a whole lot of information known about them. A scientist by the name of Bayer proposed relative stability of the various cycloalkanes based on their bond angles. So knowing that carbon likes 4 bonds and a tetrahedral arrangement of atoms, that leads to bond angles of 109.5 degrees. So if the ideal carbon bond angle is 109.5 degrees, then looking at the angles of regular polygons should give us information on the relative stability of the corresponding cycloalkanes. So he proposed that cyclopropane with forced bond angles of 60 degrees would be really, really unstable. Cyclobutane, 90 degrees, would still be very unstable. He proposed that cyclopentane with bond angles of 108 degrees, so close to 109.5, he thought this would be the most stable. And then he proposed that larger and larger polygons, because they're getting to larger and larger angles, that they would be increasingly unstable, and that this would be the most stable, everything else would be less stable. But a hypothesis is only as good as the experimental evidence to support or refute it. So by looking at the heat of combustion of a variety of cycloalkanes, we can see that these numbers increase. Well, of course they do, because we have different numbers of carbons. So comparing heat of combustion for different size molecules doesn't really help us. Instead, if we look at the heat of combustion per methylene unit, so here we have 3 CH2s, divide this by 3, we get 697. Here we have 4 CH2s, so this heat of combustion gets divided by 4, this gives us 681. So by looking at the heat of combustion per methylene, now we have values that we can compare. And what does the experimental evidence tell us? We see that cyclopropane has very high heat of combustion, therefore it starts out at very high energy and it must be very unstable. That makes sense. Cyclobutane is a little bit lower in energy, so that fits with Bayer's hypothesis. Cyclopentane is more stable, that fits with Bayer's hypothesis. But now when we get to cyclohexane, Bayer proposed that this would be more unstable because of the bond angles, yet experimental evidence tells us that it's actually more stable. If we continue to look at the larger cycloalkanes, again, instead of following Bayer's hypothesis where these would continue to increase, they really kind of settle out, and they're very, very similar to each other. So not the drastic increase that would be expected as we continue to go toward larger and larger bond angles. So as we think about Bayer's hypothesis regarding ring strain, it is a great example of the scientific method where we have a hypothesis and then there's experimental evidence that can refute the hypothesis, which means there has to be another explanation. A revised explanation is that these molecules are not flat. For Bayer's hypothesis, that was really based on the assumption that all of these molecules would be completely flat, having 108 degrees, 120 degrees bond angles. That's not what is seen experimentally, so that means that these molecules do not exist in a flat arrangement. Instead, they must take on a different type of conformation. So in our next videos, we are going to take a look at the conformations of a few cycloalkanes so that we can come to an understanding of why cyclohexane is the most stable.